Alrighty, so today we are going to tackle a problem in Chapter 15. This time it's going to be on electric fields, so this is our electrostatics chapter. For those of you following along, we're on page 523, problem number 31. Here's the figure that I already drew for it, and you'll see that in your book as well, and so I'll just read it quickly. So in this figure, determine the point other than infinity at which the total electric field is zero. So to do that, we are going to sum up the electric fields, and we're going to have two sources of electric fields because we have 2 point charges here. And there's going to be a point somewhere that we can place on this figure at which the pull from these two different charges on a test charge is what it's called. If the pull from the test charge, it's going to cancel out and it's going to be zero. So really quickly, the reason why they say don't choose infinity is because at infinity, all electric fields are zero, and so technically infinity is a point at which all the electric fields are zero, but they don't want you taking the cheap way out. So, to get started, we want to sort of rule out some places where the point couldn't possibly be. And there are a couple things that we can do. So we have sort of 3 general regions. This region over here to the left of both charges, this region here in the middle, and this region here to the right of the charges. And I'm going to narrow it down to just one of those regions, and the way I'm going to do it is only specific to this problem. So for a different problem, it might end up going into a different region, and you'll have to look at different circumstances. So I'm first going to look at the middle problem. And so if I place a test charge right in the middle here, I know that the electric fields are where a positive charge would go. So I know that a positively charged particle right here, the electric field from our positive 6 microcoulomb charge would bring it that way, to the left, and the negative would also, the charge from the negative 2.5 microcoulomb would also bring it that way. So here we see that if we place a charge anywhere in the middle, no matter what's going to happen, if it's a positive charge, it's going to go all the way to the left, and if it happened to be a negative charge, which we're not measuring, the opposite would happen, it would go to the right. Either way, the electric field's not going to be zero, so we know we're not looking at the middle. If we look at the right, and we place a charge over here, if we look at our positive 6 microcoulomb charge, that's going to give us an electric field going to the right, and our negative 2.5 microcoulomb charge is going to give us one that's going to the left. And so initially this looks like it could be a potential candidate, but now we look at the magnitude of our charges. This one is negative 2.5. The magnitude is 2.5 microcoulombs, and this magnitude is 6 microcoulombs. And since the force and the electric field here are inversely proportional to distance, meaning that the closer you are, the stronger it is, we know that if we're closer to the 6, that if we're closer to the 6, because we're on the right side, the plus 6 is always going to win out and beat the negative 2.5. No matter how far to the right we go, as long as we're still to the right of the positive 6 microcoulomb charge, our test charge is going to be pushed to the right because the plus 6 is so overpowering that it will overcome the negative 2-point charge no matter where it is placed, if it's placed to the right. So that leaves us our only option with the left over here. And one other thing is, I've been placing them only along this line, and not just because it's extremely convenient, but it turns out that if we had a test charge here, in order for 2 vectors to cancel out, because we're essentially going to have 2 vectors, because our electric field here is a vector, in order for 2 vectors to cancel out, they have to be pointing in opposite directions. There's no other way around that. If you have 2 vectors, you can't have a vector going like this, and then you can't have this vector and this vector. No matter what their magnitude are, they will never cancel out, so that will not work. So we know that it has to be along the same line, because that's the only way that the electric fields could possibly cancel out. So we know that we're going to be to the left of it. And so I'm going to place a charge, a little point here, to sort of give us a reference. But we don't know how far to the left of it. Maybe it's pretty close, or maybe it's much further away. Just to confirm that we are on the left, a positive charge is going to be pulled this way by the negative 2.5 microcoulomb charge, and it's going to be pushed away by the positive 6 microcoulomb charge. Again, because the plus 6 is further away than the 2.5, it is possible now that there's a point on here where the distance compensates for the fact that there's a difference between these two charges. Whereas again, on the right side, there was no distance at all that could possibly compensate for the difference in the charge, because no matter what happens, you're always closer to the plus 6 than the 2.5, and so that compounds the fact that the plus 6 is already going to overpower it. So now that we're over here, we need to figure out just how far away we are from this 2.5 microcoulomb charge. And we're going to call that a distance of x. So we have a distance of x, and we know that we're looking for the electric fields to equal 0. So the summation of our electric field is equal to 0. I also know, given that the direction of these two electric fields are going to be opposite, that the electric field from the negative 2.5, so the E on the negative 2.5, plus the E on the positive 6, is going to equal 0. So that's just summing up our electric fields, and these are still vectors, and we like to put on the hats because we're cool. So these two vectors adding up, they're going to cancel out to be 0. Since they're acting in opposite directions, since I need to align them to be in the same direction to be able to add them, I can actually make this a minus sign, because they're going to be in opposite directions. So we know that the magnitude of our electric field on from the negative 2.5 charge, the magnitude is going to equal the magnitude of our positive 6 charge. And that's just our vector work getting those electric fields to cancel. So now we're going to plug in our formulas. The electric field formula up here is the coulombic force. That gives us our vector here, divided by the magnitude of the test charge. And the reason they divide that out is because it needs to be able to be any charge. So the units here are going to be in newtons per coulomb. If you plug in the formula for force, you'll divide out that test charge, and you'll get kq over r squared. So let's set those equal to each other. So over here, we have k, and then our q on 2.5 is going to be none other than 2.5 microcoulombs, all over r squared. And so the distance that our charge is from the 2.5 microcoulomb is going to be x right here. That is the distance that we said it's going to be, and that's the distance that it will be. And then we'll have a similar idea for the other charge, for the other electric field. It's going to be, our charge is going to be plus 6 microcoulombs. And we're ignoring the pluses and minuses because we're putting them in opposite value signs. Because right now we're working with magnitudes, and we'll get back to the direction later. So we need a distance. And so the distance from the 6 microcoulomb charge to this test charge is going to be 1 plus x, because these charges started out 1 meter apart. And so you need to add that 1 meter in addition to however far that charge is, the test charge is from our negative 2.5 microcoulombs. So 1 plus x squared. And now at this point, it's just our math skills. We're going to solve for x. I see that we can cancel out these k's. It's much nicer than actually plugging in the 9 times 10 to the 9. And so we can also cancel out microcoulombs. And so I will cross multiply 2.5, 1 plus x all squared equals 6x squared. Just be careful with your math here, and then you'll just be fine. So 1 plus x all squared is going to get us to, and then I'm going to divide that 2.5 out. It's going to be 2.4x squared. And then I'm going to FOIL this squared out and then combine our terms. And so you'll get 1.4x squared minus 2x minus 1 equals 0. And so from this point, you can use any of your strategies. It looks like quadratic formula is going to be the easiest one to do. And so you will get two answers. You'll get that x equals 1.8 or negative 0.39. And so we have two solutions. So we ask, well, which one of them are we going to use? First off, we want to note that our answers are going to be in meters, because we used meters in our distance, and that's going to be our standard unit since we were using newtons. Newtons is going to give us our answer in meters, so we want to make sure that we stay in meters here. So we have 1.8 or negative 3.9. And so since we're working with distances, you're already going to get the idea that we're going to take the positive answer of 1.8. And that is going to be the final answer of 1.8 meters. So our test charge is going to be 1.8 meters left of this 2.5 microcoulomb negative charge over there. That's the point at which the electric fields all cancel. And you can throw away this negative 0.39. What that actually means, it's not completely meaningless. What that actually means is that because the quadratic formula and the absolute value signs took away the directionality and the positive and negative aspect of the charge, what that actually means is that if this were a positively charged, and it were positive 2.5 microcoulombs, or if both of them were negatively charged, then it turns out that the point you'd actually want to go to would be actually negative 0.39 meters left. Negative 0.39 meters left is actually 3.9 meters right. So this is where you'd go if these were the same charge, and this is where you'd go if they're different charges. And so since they're different charges, you could actually switch the positive or negative, and this would still be the exact same point that it would go to. And it also doesn't matter what kind of charge you place there because these are electric fields, they're newtons per coulombs, and we picked a point and we didn't pick a charge. So 1.8 meters is our final answer. I hope that helps, and thank you for watching.